Welcome back. Today, we're going to take everything you know about calculus on a nice flat plane, and we're going to give it a whole new dimension. We are making the jump from 2D to 3D space, and trust me, this is where things get really interesting. So here's the game plan. First, we'll officially welcome you to the third dimension. Then we'll get you geared up with a new 3D toolkit. After that, we'll look at the crazy way a circle can become a cylinder. We'll run through some examples to see it all in action, and then we'll wrap up with the key things you've got to remember. All right, let's do this. First up, welcome to the third dimension. We're not starting from scratch here. We're going to build on everything you already know about that familiar 2D plane and use it to launch ourselves right into 3D space. Think about it. In 2D, you've got your classic X and Y axes, right? Well, to get into 3D, all we're going to do is add one more axis, the Z-axis, and have it stick straight out, perpendicular to the other two. It's that one simple move that completely changes the game. So this new Z-axis doesn't just give us height, it creates whole new planes to work with, the XZ plane and the YZ plane, along with the XY plane we already had. And you know how you had 4 quadrants in 2D? Well, these 3 planes slice up space into 8 different regions, and we call those octants. Okay, so to move around and actually do stuff in this new 3D world, you're gonna need some tools. Let's stock your new 3D toolkit with the 2 most important formulas you'll be using. First up, the distance formula. And hey, this should look super familiar. It's really just the Pythagorean theorem you've been using forever. We're just adding one little piece for that third dimension, this z-squared term right here. It's a totally logical, beautiful upgrade. And it's the same story for the equation of a sphere. This is just a direct promotion from the 2D equation of a circle. You've got your center at HKL and your radius r. The only new part is this little z minus L squared term. See? It's that simple. All right, now for a concept that might feel a little weird at first. This is where things get kind of mind-bending, because equations you thought you knew, well, they take on a whole new life in 3 dimensions. So let me ask you this. What does x squared plus y squared equals 4 represent? Now, in your 2D class, you'd shout, a circle with a radius of 2, and you'd be 100% correct. But what happens when we're playing in R3, in 3-dimensional space? And here it is, the big reveal. In the 2D plane, it's a circle, no doubt. But in 3D space, that exact same equation describes an infinite cylinder. So how on earth is that possible? Let's dig in. Here's the secret sauce. Look at that equation again. X squared plus y squared equals 4. Notice something? The variable z is totally missing. It's not there. And in the world of 3D, if a variable isn't mentioned in an equation, it means it's a free agent. It's completely unrestricted. Z can be any number at once, which means we can take that circle and just stack it over and over, up and down the z-axis forever. This table is basically your new cheat sheet for interpreting 3D equations. If you lock down one variable, like saying x equals 3, you get a flat plane. If a variable is totally missing, like in our cylinder example, you get this extended shape. And if all 3 variables are in there working together, well, then you're describing some kind of surface, like a sphere or maybe a tilted plane. Okay, enough theory. You get the ideas. Now let's see how this all comes together to solve some actual problems. It's time to get our hands dirty and put these concepts to the test. First up, a nice, straightforward distance calculation. We're just going to plug the coordinates from points P and Q right into that 3D distance formula. Now, word of warning, a super common mistake happens right here with the y-coordinates. You have -3 minus a -1, which becomes -3 plus 1. Watch those double negatives. They'll get you every time. Once you get past that, you just simplify, and bam, the distance is 3. This one's a classic. They give you this messy-looking equation, and you have to figure out the sphere's center and radius. The name of the game here is completing the square. So first, you group your x's, y's, and z's together. Then you work your magic to complete the square. Now, here's the absolute golden rule. Whatever you add to the left side of the equation, you must add to the right side too. You got to keep it balanced. It's so easy to forget that step. So, after you've grouped your terms and you've completed the square, your messy equation turns into this much cleaner, much friendlier version. And now you can just read the answer right off the screen. The center is at -2, 3, 0, and the radius is the square root of 13. All right, last example.
We need to describe the graph of y equals 2x minus 1 in R3. Now, in 2D, that's just a line, easy peasy. But in 3 dimensions, what's the first question we always ask? That's right, which variable is missing? It's z. And because z is unrestricted, we just take our 2D line and stretch it up and down forever along the z-axis. And what do we get? A vertical plane.
All right, that was a pretty fast trip through the third dimension. So let's slow down for a second and just nail down the most important things you need to walk away with from this explainer. Here are the big ones. First, going to 3D is as simple as adding that z-axis. Second, those key formulas for distance and spheres, they're just souped-up versions of the 2D formulas you already know. But third, and this is the real mind-bender, when a variable is missing from a 3D equation, you take the 2D graph and just extrude it, or stretch it, along that missing variable's axis. And that's the whole secret to how a circle magically becomes a cylinder and a line becomes a plane. And that just about does it for us. We've seen how just adding one little dimension can totally transform the things we thought we knew. So I'm going to leave you with a question to chew on. If we can create these incredible infinite shapes just by leaving a variable out in 3D, what kind of wild things could we create if we did the same thing in 4 dimensions? A hypercylinder, maybe? Just something to think about.